December 7, 1941. The United States was thrust into a conflict that would demand the largest industrial mobilization in human history. Shipyards roared with steel presses, airplane factories hummed with assembly lines, and chemical plants pushed out explosive tons by the hour. But behind the headlines of tanks and bombers, another silent battle was underway, a battle fought in the hearts of massive generating stations. Engineers across the country were given a task that few civilians understood fully: build power plants that could not fail. Not for months, not for years, but for decades. These were plants intended to supply energy to munitions factories, military bases, and industrial cities that had to run continuously. Every boiler, turbine, and feedwater pump had to withstand the demands of war: high loads, unrelenting pressure, and round-the-clock operation. No corners could be cut. There was no margin for the failures that might delay production of engines for tanks, aluminum for airplanes, or steel for ships. Materials were scarce, labor was stretched thin, and timelines were tight. Yet the engineering community responded with ingenuity that bordered on obsession. The boilers were built thick, massive walls of steel designed to contain steam at pressures higher than most civilian plants had ever dared. Turbines were oversized, their rotors heavy enough to store enormous amounts of kinetic energy, capable of smoothing the uneven load fluctuations that came from factories running day and night. Every valve, every pump, every mechanical linkage was built not for economy, but for endurance. Engineers studied thermal stresses, metal fatigue, and vibration patterns with meticulous attention, ensuring that nothing would give way when the plant was under the heaviest possible loads. By the end of the war, hundreds of these plants dotted the American landscape. They were symbols of industrial might and engineering foresight, monuments of steel and concrete that reflected a philosophy that the modern era of build cheap, build fast would soon abandon. Walking into a 1940s power station was like stepping into a cathedral of steel and steam, a space where human ingenuity met brute mechanical force. The steel boilers, some tens of feet in diameter, towered above the floor like industrial skyscrapers, their riveted shells gleaming under the harsh glare of overhead lights. The turbine halls echoed with the deep, measured hum of slowly spinning rotors, each 100 tons of steel suspended with meticulous precision, turning at a deliberate pace that seemed almost ritualistic. Every rotation was a dance of mass and motion, converting heat into electricity with an elegance that belied the raw power coursing through the plant. Nothing moved faster than it needed to. Every pipe, beam, and valve carried more weight, more thickness, and more redundancy than the engineers expected to ever use. Feedwater pumps were cast iron, often so massive that a single valve weighed more than a modern pump assembly. Even the flanges connecting sections of pipe were oversized, with bolts spaced generously to prevent stress concentrations, while layers of insulation and protective steel jackets wrapped critical conduits, allowing them to withstand surges in pressure that would snap modern thin-walled systems in an instant. The boilers themselves were engineered to endure overpressure, corrosion, and decades of thermal cycling, with walls several inches thick and rivets set in patterns designed to distribute force evenly. Control rooms reflected the same philosophy. Unlike the compact, computer-driven control centers of today, these rooms were simple, mechanical, and intuitive. Levers, dials, and gauges allowed operators to feel the heartbeat of the plant. A trained engineer could walk the floor and diagnose the health of the entire station by observing a lever's resistance, the faint vibration of a turbine shaft, or the subtle hiss of steam through a pressure valve. The plant was designed not to hide its workings behind screens or automation, but to make them legible, readable, and maintainable. A machine that invited human understanding rather than demanding blind trust in electronics. Even the smallest details reflected this obsession with permanence. Bearings were oversized, built to distribute wear evenly across massive contact surfaces, ensuring they would survive decades of friction. Lubrication systems were often redundant, with pumps and reservoirs that could maintain flow even if one unit failed. Each mechanical link, a rod, a coupling, a pin, was engineered to accommodate thermal expansion, vibrations, and decades of heavy use without yielding. Structural steel beams, often layered and cross-braced, could carry far more weight than anticipating accidental overloading or unforeseen stresses. Redundancy was built in at every level. Engineers of the era seemed to operate under a single unspoken principle. It was better to be overbuilt than underprepared. Safety margins were not mere percentages calculated to meet regulatory minimums. They were multiplied by 2, 3, or more, providing an invisible insurance policy against decades of wear, abuse, and unexpected events. Modern engineers, accustomed to digital monitoring, finite element modeling, and lightweight alloys, often marvel at the resilience of these old stations. 50 years, 60 years, 70 years of continuous service were the rule rather than the exception. This philosophy extended beyond individual components to the system as a whole. Piping runs were deliberately oversized to reduce velocity and stress on joints. Valves could be replaced without shutting down critical operations. Turbine rotors, enormous and slow-turning, were paired with massive flywheels that stored kinetic energy, smoothing fluctuations and protecting the plant from sudden spikes in demand. Steam lines were routed for easy access, allowing maintenance crews to inspect, repair, or replace components without dismantling entire sections of the station. Every inch of these plants reflected forethought, an anticipation that humans would be operating and maintaining them for decades, and that the machinery itself must survive that human stewardship without compromise. Walking through these halls, it became evident that the engineers of the 1940s were building more than a power station. They were building permanence. Each bolt, each steel plate, each turbine rotor was a deliberate rejection of expedience. Where modern plants often prioritize efficiency, cost savings, and compactness, these stations prioritized resilience, predictability, and longevity. They were not elegant in the sleek, minimalist sense. They were monumental, unapologetically massive, and meticulously precise. And the proof was in the decades that followed. These plants, overbuilt and over-engineered, survived repeated cycles of heat, pressure, and use that would cripple modern installations in mere years. Boilers aged without warping, rotors spun for decades without catastrophic fatigue, and simple mechanical designs allowed operators to keep plants running when newer high-tech facilities were sidelined by electronic failures, microfractures, or oversensitive sensors. Every component was a testament to a philosophy that valued permanence over profit, durability over speed, and resilience over style. Walking into a 1940s power station, one could almost hear the lesson whispered in the hum of turbines and the hiss of steam. Overbuild, over-engineer, and design for generations, not just for the next budget cycle. In these halls, steel and iron did not merely serve, they endured. One of the most striking differences between 1940s power plants and modern facilities was the philosophy of rotation, the very heartbeat of these industrial giants. Turbines turned slowly, deliberately, almost meditatively, with enormous thermal mass that allowed them to absorb stress, temperature fluctuations, and load variations without risk of catastrophic failure. In modern plants, turbines often spin at tens of thousands of revolutions per minute, their lightweight blades delicately balanced to extract every ounce of efficiency. In the wartime-era plants, speed was sacrificed for stability. Mass was preferred over thin, high-tech alloys. Vibrations were not countered by sensors and digital damping systems. They were tamed through sheer weight, through the brute physics of tons of steel and iron moving with deliberate grace. Walking across a turbine hall, one could feel it, the subtle sway of a 100-ton rotor suspended above the floor, a pendulum of energy, its momentum absorbing shocks invisible to the human eye. The rotors themselves were forged with enormous tolerances. Each blade, each journal bearing, each coupling, was designed to flex slightly under extreme conditions, taking advantage of mass to mitigate the stress that would instantly fracture modern, lighter components. The flywheels alone were engineering marvels, massive discs of steel that stored energy and rotational inertia, acting as buffers during sudden surges or drops in electrical demand. A spike in load did not shatter the plant. It rippled gently through the machinery, absorbed, redistributed, and smoothed by sheer mass. Steam systems mirrored the same philosophy. Oversized pipes, boilers, and valves were deliberately designed to outlast decades of continuous operation. Thick insulation preserved heat, and oversized conduits allowed pressure to fluctuate without inducing dangerous vibrations or overloading sensitive components. When a wartime plant faced a sudden ramp-up in electricity demand to feed a munitions factory or a military base, the system responded like a seasoned athlete, flexing but never breaking, its thermal mass acting as a shock absorber across hours of operation. In contrast, modern high-speed turbines rely on delicate electronic monitoring and precise control loops, leaving little room for human operators to compensate when sensors fail or unexpected loads occur. The benefits of slow-turning, heavy-mass design were not theoretical. They were proven day after day, decade after decade. Bearings that would have burned out in modern high-speed systems continued to operate for tens of thousands of hours. Lubrication systems, oversized and redundant, ensured that friction never became a limiting factor. Large-diameter turbines and massive casings allowed thermal expansion to occur gradually, preventing microfractures in the metal that might cripple a modern lightweight rotor. Even the plant floor seemed to participate in the strategy. Massive. Steel foundations dampened vibration, while flexible mounting points allowed movement without transmitting stress to sensitive machinery. Engineers of the era understood something modern designers often overlook. Efficiency could always be sacrificed, but reliability was sacred. A plant that failed during a wartime munitions run could cost lives, delay production, and disrupt entire military operations. Every engineering decision, from material thickness to rotor speed, from valve sizing to thermal expansion allowances, reflected this understanding. Designers deliberately overbuilt components to survive events no one could predict. Voltage spikes, sudden steam shortages, extreme cold, or summer heat that would send pressure soaring through boilers. The philosophy was simple. A plant must endure, first and always. Even in peacetime, these principles paid dividends. Many of these turbines, rotating slowly with their enormous flywheels and oversized components, remained in service for half a century or more. By the time electronic monitoring and computer-controlled systems became standard, these plants had already proven their ability to endure decades of thermal stress, mechanical fatigue, and human operation without catastrophic failure. Modern turbines, by contrast, might achieve higher efficiency on paper, but their reliance on speed, lightweight alloys, and automation made them fragile, prone to cracking, overheating, or failure when conditions deviated even slightly from design parameters. In essence, the philosophy of slow turns and heavy mass was a lesson in patience and brute engineering wisdom. Where modern design sought speed, compactness, and theoretical optimization, wartime engineers demanded resilience, redundancy, and permanence. Each rotation of those massive rotors was a silent testament to a time when mechanical mass was trusted over electronic oversight, when the laws of physics were leveraged to guarantee decades of continuous operation, and when reliability, not efficiency, was the ultimate metric of success. In these 1940s power stations, simplicity was not a compromise. It was strength. Every mechanical layout was deliberate, every pipe and valve positioned with purpose, yet uncomplicated enough that any trained operator could understand the entire plant at a glance. Pipes ran in predictable grids along walls and ceilings, neatly color-coded or labeled, tracing the paths of steam and water like arteries and veins through the facility. Pumps, turbines, and boilers were arranged for accessibility, and maintenance crews could disassemble almost any piece of equipment with hand tools without the need for specialized wrenches, proprietary parts, or digital passwords. The plant was a machine whose inner workings were meant to be seen, touched, and understood. There were no black boxes, no microprocessor-controlled valves, no software patches that might fail without warning. This simplicity translated directly into resilience. Cast-iron feedwater pumps, some installed in 1943, could be serviced, repaired, or even rebuilt on-site without shutting down the entire station. Steam traps and relief valves could be replaced while the system continued to operate, and operators knew which parts could fail safely without endangering the plant. Redundancy was built into every system. Parallel pumps, duplicate steam lines, and bypass loops meant that one component's failure rarely stopped production. In wartime, when electricity powered critical factories, munitions plants, and hospitals, this reliability was essential. Engineers understood that failure was not an option. The advantage of simplicity was not merely convenience, it was strategic. Heavy-duty mechanical systems could absorb misuse, stress, and decades of operation with minimal intervention. Bearings could be re-greased, valves reseated, and pipes realigned, all with minimal downtime. A single maintenance crew armed with skill and experience rather than diagnostic software could keep the plant running through storms, equipment fatigue, and even the occasional operator error. The very design invited human oversight, trusting engineers to read the system as if it were a living organism, to anticipate problems, intervene before disaster, and keep energy flowing reliably. Contrast this with the design philosophy of modern power stations, where efficiency and compactness often take precedence over durability. Today, thin-walled turbines spin at high speeds. Welded piping carries superheated steam under pressure, and digital controls manage every aspect of operation. One misconfigured sensor, one microfracture, one software glitch can trigger hours of downtime, forcing extensive repairs and complex diagnostics. Modern systems, while technologically advanced, are fragile ecosystems, high-performing but easily disrupted, dependent on electronics, automation, and specialized knowledge that can be lost or compromised. The engineers of the 1940s understood something that contemporary designers often overlook. Durability does not emerge from cleverness, sophistication, or automation alone. It comes from materials that can withstand stress, mechanical mass that can absorb shocks, and layouts that humans can interact with intuitively. A simple valve, a heavy cast-iron pump, and a predictable grid of pipes can deliver far more reliability than 1,000 lines of software or a complex digital control system. When complexity is introduced, failure modes multiply. When simplicity reigns, resilience endures. Walking through these old turbine halls, one can almost feel the design philosophy embedded in the metal itself. Every accessible shaft, every serviceable valve, every mechanical linkage radiates a quiet confidence, a declaration that the plant will continue to operate, come what may. Over decades, even as technology advanced and newer, faster, sleeker plants were built, these wartime-era stations continued to hum, serving communities, industries, and even whole regions without the catastrophic failures that often plague modern facilities. In essence, The 1940s power plants were lessons in longevity. Their mechanical simplicity was not naive. It was calculated, deliberate, and proven over decades. Mass, accessibility, and redundancy created an infrastructure that could be maintained, understood, and repaired by human hands, ensuring that energy continued to flow even when the unexpected occurred. Where modern plants often rely on invisible software and delicate materials, the wartime engineers trusted steel, cast iron, and human skill, a combination that kept their machines alive for half a century or more. Real-world examples of these plants demonstrate their extraordinary longevity. The Schenectady Steam Station in New York, built in 1942, remained operational for more than 60 years, its original turbines and boilers running reliably long after newer plants in nearby regions struggled with chronic breakdowns. The Patterson Generating Station in Pennsylvania, built during the same period, required only routine maintenance to keep its massive steam turbines functioning at peak performance for over half a century. Operators and engineers often marveled at the predictability of these machines. Steam pressures remained consistent, vibration levels stayed within safe limits, and heavy cast components showed minimal wear. Maintenance crews, trained to understand mechanical systems deeply rather than rely on automated diagnostics, could anticipate problems before they occurred, replacing worn parts in a methodical and planned manner, rather than reacting to sudden failures. When modern plants are compared directly, the differences are stark. Thin, welded steel and aluminum components are prone to fatigue cracking. Electronic systems, while precise, are vulnerable to surges, corrosion, and obsolescence. Whereas wartime plants could often be kept online indefinitely with competent crews, contemporary facilities sometimes fail within decades, requiring expensive retrofits or complete replacement. The lessons are clear: overbuild, allow for mass and inertia, and prioritize maintainability over short-term efficiency. Building these plants during the 1940s was expensive. Material costs were high, labor was intensive, and schedules were tight. Yet the economic calculus of the time justified the expense. A plant that lasted 50 or 70 years required fewer replacements, fewer repairs, and fewer interruptions to energy production. When considered over decades, the higher initial investment paid dividends that modern cost-cutting strategies often overlook. Modern engineers, under pressure to reduce capital costs and maximize efficiency metrics, often choose lighter materials, welded joints, and computerized controls. These strategies can reduce initial expenditures, but often lead to a hidden long-term cost: fragility. Cracks in thin metal, corrosion in cheap alloys, and failure of proprietary electronics accumulate over years, forcing unplanned shutdowns, costly repairs, and premature replacement. In contrast, the 1940s plants built with mass, thick steel, and redundancy rarely required major intervention. Their simplicity and overbuilt design created a resilience that modern optimization cannot replicate easily. The plants of the 1940s stand today as monuments to a philosophy largely abandoned in modern engineering. That infrastructure, when built to last, can serve generations. Engineers continue to study these facilities, examining why turbines that spun for decades with minimal maintenance can outperform modern equivalents plagued by constant electronic and thermal failures. The legacy is both technical and philosophical. Heavy materials, simple mechanics, slow-turning turbines, and overbuilt components created systems that were forgiving, maintainable, and enduring. They remind us that engineering is not merely about efficiency or speed, but about foresight, endurance, and reliability. The world has advanced in complexity, automation, and energy density, but the lessons from these wartime power plants endure. Sometimes, The longest-lasting systems are those built not for cost savings, not for elegance, but for pure, uncompromising durability. In a modern era obsessed with cutting corners, micro-optimization, and instant replacement, the 1940s power plants remain a testament to an approach that valued permanence over expedience, mass over fragility, and engineering excellence above all. Their turbines still hum in memory, a reminder that some systems, when built to last, truly can outlive entire generations of the technologies that follow.